Dear conference listeners, hello. My name is Lukas Daubner, and I'd like to present you the work Risk-Oriented Design Approach for Forensic Credit Software Systems. But first, let's start with what are the forensic credit software systems. You might be familiar with forensic readiness, which is an approach to prepare in advance for eventuality of forensic investigation. Now, we want to approach it from the software engineering perspective, in a way that we aim to design the systems and make them forensic ready. Like we can do this with security or privacy. So then we take forensic readiness as a non-functional software requirement, and therefore we complement this existing state-of-the-art in forensic readiness. So the aim is to design a system to produce sound evidence, handle it in a sound way, and assist during the investigation. So, to explain myself, let's look at an example of scenario of some software system. And this is automated valet parking, issuing a permit, and this is BPMN diagram. You can see here user login, where user logs in the system. The credentials are checked against some database, and then the system will check the availability of free space on the parking slot. If there is some request to pay, and then the reservation ticket is generated, which is then stored in the user device to be used later at the parking lot. So if we look at the system, what can we see from the perspective of forensic readiness? Is there any kind of evidence that would help us during the investigation? Well, we cannot really use user device because that belongs to user, but we can look at our system, and there are two databases. But unfortunately, as I'm going to show you, they will not help us. So let's take a look at an example of attacks. First, we got this attack of falsifying availability reports, when some malicious entity wants to send false reports of availability to make it look like the parking lot is full and therefore no reservation can commence. Similarly, fabricating a parking permit, some malicious entity wants to insert a ticket without paying to the parking lot to gain access, and here we are interacting with this database that could tell us something. However, the database itself cannot distinguish between what is real and what is this fabricated ticket. Then we also can have fake payment issued. So user receive a fake payment request on our behalf, which will go to the account of malicious attacker, and then from the user side also the user can repudiate its parking ticket and demand refund. So want to protect against these attacks, and you may say, yes, let's employ security in the first place. And I agree with you, because even though we cannot detect these attacks or misuse, we can apply security measures to protect ourselves. But there's a problem. Security is never 100%. Sometimes, even if we apply security, there are some weak spots. And many times, even the security measures are not applied because of the cost, because of the interference with other parts of the system, or the attack has just low probability to happening. And then we get this human aspect when an insider with legitimate access can use the system for nefarious means. So let's consider the forensic readiness as an enhancement to security. We build on the top of already secure systems and try to make it better. Therefore, we proposed this novel risk-oriented forensic credit design, because risk management is a well-known approach in cybersecurity. We want to assess risk and the treatment to allow more informed decisions about forensic ready controls. There's two parts. One is the process, and second is the modeling phase, which I will go through now. So this is the process, core of our approach, and as I mentioned, it assumes that the cybersecurity risk management was done previously. First, we want to identify some background and foreground evidence based on what we already have and describe those sources. Then, going through that, we review, and this is an iterative process, we review all the risks from previous steps. So, if there is some retained risk, we may use forensic ready means to mitigate it. Maybe there is some residual risk, so we want to look at it as well. And of course, there's this problem of unknown risk, where we aim to make the attacker noisy, to leave the traces behind. So we are searching for these cases. And also, we want to look at disputes. This is more of a business risk than a security risk, but still, a user may place a dispute over some asset, or we need some evidence that to dispute something ourselves. For example, tampering, non-existence of some asset, or if there is, for example, contract breach from third party. So we want to have evidence for it. And then, based on this part of iteration, we want to introduce new forensic sources, and describe them, and iterate again if needed. And to support this process, we have this forensic ready BPM annotation. This is, again, some novel notation supporting this process, and it aims to capture sources of potential evidence and their relationship. It assists in this risk treatment re-evaluation phase. So let me show you an examples of based on the scenario I presented before. So let's consider this denial of service. We mitigate this attack, as you can see highlighted in blue, by public key cryptography. But then the key can be reverse engineered. So we introduce logging to detect discrepancies. And not only that, these logs have a relationship because they depend on each other. And this notation can highlight this. Similarly, parking permit fabrication. There can be this issue, attacker directly insert into the store fake parking permit. Again, we aim to mitigate this by securing the storage. But again, insider can still insert this ticket. So therefore, store auditing help us with detecting suspicious behavior. And you can see it on the bottom, where you have the store and highlighted storage log as our piece of evidence. Then for the access control, again, attacker might insert the permit by bypassing the access control which we implement before. And if you can see on the button, again, we want to employ access control auditing to see who is accessing and if there is some problem. For example, attacker could insert himself or herself to this credential store. By issuing a fake permit, we might retain say, log of requests, history of requests. This risk was previously retained due to low probability of happening because attacker need to access a PSP private key, which is pretty well secured, but still there is this possibility. So how do we avoid that? Or avoid that, detect that is the better word. We keep the history, and also we keep the integrity of the history by trusted timestamp. And you can see it on the picture. There's a relationship hardening, which means the trusted timestamp hardens the previous evidence by providing proofs of integrity. And lastly, example for dispute. The dispute itself is not really covered by security, it's more like a business risk. But still we can model it and we can gather the evidence. This is a little bit tricky because we don't have access to the user device, so we need to have sufficient proof in our system without interacting with the user. And then we choose to make the permit in 2 locations, which will be harder to falsify, and again keep the integrity hardened as in the previous case, and you can see it up here. So to conclude this talk, forensic software systems aim to produce sound digital evidence and handle it in a sound way and assist the investigator or the persons involved with in a forensic investigation with a task. A risk-based process to identify and manage this forensic credit controls. We proposed this novel approach, and also the BPMN notation to support this. And now, this is the end of the presentation. I thank you for your attention, and I'd like to invite your questions.